all the programs we have seen so far consisted of a main function that was using functions from C's standard library to perform its job. We're now going to consider programs in which we write custom functions, meaning our own functions. So in the first example, we're going to write a program that has a custom function called square. And what this custom function does is it takes as an argument an integer and returns the square of that integer as a return value. And we're going to use the square function for all the integers from 1 to 10. This is the example program. Again, the new parts are highlighted in yellow. And we have a main function over here with a for loop that runs for 10 times. As you can see, x is the counter variable, the loop control variable, going from 1 to 10 at increments of 1. Inside the for loop, we have a printf statement. And that printf statement prints out the return value of the function square, which takes as argument the value of x. Now the program begins, of course, with the start of main. We enter the for loop, and inside the printf statement we are calling the square function. What happens then is the value of x is copied into a new variable, a new integer variable y. And this integer variable y exists only inside the function square. Inside the function square, we compute y multiplied by y, and that value, that integer value that square returns, is returned by this call to the function square and is printed out by the printf statement. Now inside, something that I want to highlight over here and that we're going to talk about in much greater detail later in this course is that it is actually that the value of x at this point is copied into another variable y that exists inside the function square. It is not the same variable. If you make changes to the value of y in here, which we're not doing in this case, but if you're making changes to the value of y, that will not affect what the value of x will be in the main function. So this is basically how you can see that the square function itself is defined down here in parallel to the main function up here. There's another new thing over here on line 5 where we have kind of a repetition, the return type of the square function, the name of this custom function, together with the list of arguments, parameters that it takes. But over here we have a semicolon after that. This line over here is called the function prototype of a custom function. I'll talk a little more about that. So it's the same explanation you just saw. Call square, the return value is printed out by printf. Inside square we calculate y times y, and of course since this printf statement is inside a for loop, this happens 10 times, each time with a different value of x. Now, the definition of function square shows that it expects as input, as a parameter, an integer, which it calls y. As you can see, the name of the variable over here is y. It's called something else over here, and that is absolutely fine. Before the name of the function, we see the data type int being mentioned, and that is, of course, what you know by now, the return type of the square function. Now, the function prototype that you saw at the top is this, and one thing to remember over here is there are no curly braces after it, instead only a semicolon. The use of having the function prototype at the top is to tell the compiler to expect to see a definition, meaning the code, of a function with that return type, with that name, with that number of arguments, and those types of arguments provided in the prototype. And of course, the arguments also have to be in a certain order. So this is the general form of the function definition, including the code, right? Function rules for function names are the same as for variables. Cannot start function names with a numeric character, and you cannot use any of the reserved keywords we have in C. If a function does not return anything, the return type is set to void. If a function does not take anything as an argument, the argument type is also set to void. Sometimes the return type, the function name, and the parameter list, also called function header. When you're using custom functions, make sure that they are returning the type of value they're supposed to. And if a function is not supposed to return anything, make sure that is also the case in the definition. You're already familiar with functions that take multiple arguments, multiple parameters. The list of arguments or parameters that a function takes are comma separated. Again, if a function does not receive any values, does not have any parameters, put in void. You have to specify the type for each parameter. So for example, if a function takes two parameters of type double, you can't just write double x comma y. That won't do. Instead, you have to specify the type for each parameter. So double x comma double y. Otherwise, you'll get a compiler error. Also, do not place a semicolon after the parenthesis when you're in the function definition. That'll also give you a syntax error. Inside a function, if you create a local variable with the same name as one of the variables in the parameters, that will also give you a compiler error. In a sense, the parameter list of the function also acts as variable definitions. Also, do not use, and that's to help avoid confusion, do not use the same names for a function's arguments and the corresponding parameters in the function definition. All the statements inside the curly braces of a function are also referred to as the function's body, or also as a code block. You cannot define a function inside another function. That's another type of syntax error. If you're unable to come up with a meaningful function name for a function, or even names for parameters of a function, it means so first of all, use you'll have to use some comments, or actually should avoid too many comments by choosing names for parameters and functions that are meaningful. Keep the size of functions small, because that means they do something very specific and those functions are more likely to be reused in other projects. A program should generally be written as a collection of small functions. Smaller functions are of course easier to write, easier to debug, easier to maintain and change or modify. If you have a function that requires a large number of parameters, that is a hint that you may be doing too many things. You may be performing too many tasks inside a function, and you should look at perhaps breaking down that function into multiple functions, smaller functions. Of course, function prototype, function header, and when you use those functions, the function calls should all have the same numbers, type, and order of arguments and parameters. And of course also the same type of return value. Now, about the return values for functions. You can come back from a function by using the return keyword. If you have nothing to return, no value to return, you just type return semicolon. If you have a value to return, if your function computed some product, some work product, you've already seen that that can be done by typing return and then whatever value you want to return, followed by a semicolon. Now, occasionally you may have a function that does not return anything. Now, the main functions that we've been using, occasionally I've been putting a return 0 at the end of that, or just a return. Even if I don't do that, what C will automatically do is it will make the main function return the value 0. But you can also return other values, of course. And if a function does not have anything to return, one thing that is often done is we use the return value to signal some kind of problem that happened inside the function, if a problem happened. And that can make it easier to debug programs. So typically a 0 means no problems, a non-zero value means some kind of problem, and different values that you're returning from the function can have different meanings as to what went wrong. So let's look at another example. This one will be a custom function that we call maximum. And what this function will do is it will take 3 integers as argument and it will return the largest of them. And this is the code. Not all of it, but over here we have right at the top the function prototype, function called maximum, takes 3 arguments of type integer, x, y, and z, and returns an integer, of course. And in the main function, we are declaring three variables of type integer, number 1, number 2, number 3. We have a printf statement followed by a scanf statement in which we receive three integers which are stored in number 1, number 2, and number 3 using scanf, or in our case, since we're using Visual Studio, scanf_s. And this is followed by a printf statement in which we print out the value returned by the maximum function, which is taking number 1, number 2, and number 3 as arguments. And now let's look at the maximum function, and that's this one. Operation is pretty simple. We define an integer called max, initialize it to whatever the value of x that we received in the first argument, and then we check if y is larger than max. If it is, max is updated to the value of y. Otherwise, nothing happens, of course. Then we check if z happens to be bigger than max. If it is, max is updated to the value of z, and we return the value of max. An integer, of course. When we run this with values 22, 85, 17 as arguments, as inputs, the return value from maximum will be 85. If we enter 47, 32, and 14, the return value from maximum is 47. 35, 8, and 79, and the result will be 79. Now, the idea of having function prototypes, this is originally wasn't in C. This is something that was borrowed from C++, and it's actually a good idea that because it helps the compiler catch more errors if there's a disagreement between the function definition and the way the function is being used, function is being called. So it's a way to validating function calls. Early on, this was not the case, which meant that you had to deal with more runtime errors. And as a matter of fact, this is a good time to talk about something else, the hash include preprocessor directive we have been using. What we've basically been doing is we've been using hash include and standard io.h file. Now, we haven't talked about that yet, but inside the header file are basically function prototypes. All the function prototypes related to this particular library, in this case, input and output. And we've been including this header file in every program because just about every program we've been using has been using input and output, printf, scanf_s, scanf. In a sense, actually, when we use hash include, what we're doing is we are inserting function prototypes of all functions mentioned in this particular header files. Header files are basically nothing but a collection of function prototypes. When we make our own function, that is of course not included in any of the header files in the standard library, which means we have to add our own function prototype, which is what we have been doing. The same thing is the case when we were using the math.h library. It is just, you can think of the hash include basically adding all the function prototypes of all the math functions in the math library. Similarly, the stdio.h function over here is basically inserting all the function prototypes of the printf, scanf, and other functions. You don't have to just because you have a function prototype declared at the top of your program doesn't necessarily mean you actually have to use that function. So you can have more function prototypes declared in the beginning. You don't have to necessarily use all of them. So in this particular example, this is the function prototype for the maximum function. Returns an integer and takes 3 integers as arguments, followed by a semicolon, not to forget. Another thing, the function prototype's basic purpose is to check all the types, number of arguments, etc. That should be expected with calls to that function. If you think about it, the names of the variables at that point are irrelevant. We still include them because because you could also write this as your function prototype. This is perfectly valid. You do not have to include the mentions of x, y, and z that we've been using. They're unnecessary, but we include them for easier reading, kind of as documentation. Again, please do not forget the semicolon at the end of the function prototype. Now you can get compilation errors when you use custom functions for a variety of reasons. Usually when the function prototype and the function definition do not agree, that can be one reason. Also when the function prototype and the call to that function, when they do not agree. When the return type does not match what's specified in the function header or function prototype. So if the prototype had been written like this, obviously our maximum function is returning an integer, but if the function prototype says void, that would become a problem. Slightly related to this are the rules of arithmetic conversion. This is basically when you have a function that takes one type of argument, but you use the function with a different type of argument. This is something that relates to numbers. So, for example, we have the square root function in the math library. Now, the square root function takes arguments of type double, and returns arguments of type double. But in this example, in this statement over here, we're providing it an integer, 4. And that is fine because when that happens to be the case, implicitly what will happen is your provided integer value will be converted to a double on the fly and then passed to the function square root in this case. If you wanted to pass an argument of type double, you would have written it as 4.0. There are some other rules associated with numeric data types, and I'm going to talk about those. So going from an integer to a double is not a problem, but let's say you have a function that is expecting an integer and you are passing it a double. That can create a problem because the fractional part of your argument will get lost. It will be truncated, it'll be dropped, lost, which means that the return value from that function may not be what it should be or what you would expect it to be. You can get similar problems when you go from larger data types to smaller data types of the same type. So for example, you have a long double and you convert it to a short. So generally, if you have an expression in which you have mixed data types, what happens is, what will happen on the fly is that the data types of all terms will be raised to that of the highest data type. What do I mean by highest data type? I'll show you in a second. So for example, among all the floating point data types, let's say one of the terms in your expression is a long double, which is like the largest type of fractional number data type we have. All other terms will also be elevated or converted to a long double first, and then the expression will be evaluated. If the highest type is a double, everything will be elevated to a double, and then the expression will be evaluated. If the highest is a float, everything will be up converted to a floating point number first, and then the expression is evaluated. Now, converting from any type of integer, any integer type, any data type that does not store fraction numbers to a floating point type, it's not a problem. Doing the reverse means you might lose data by truncation. And here is a table that shows you the different data types for floating point types and integer types, from lowest to highest. Lowest to highest. So at the bottom we have character, only 1 byte long, followed by short, unsigned short, int, unsigned int, long int, unsigned long int, long int, unsigned long int. For floating point numbers, we have, it's rather straightforward, float, double, and long double at the very top. Now, the conversion from a lower data type to a higher data type, that happens implicitly. If you need to do the opposite, if you need to go from a higher data type to a lower data type, that is something that you have to do explicitly using casting, which we already used before. So let me give you an example. For example, square function over here uses an integer parameter. If you call it with a floating point argument, such as the value 4.5, it has to be converted to the lower data type int, because that's all the square function will take. 4.5 as a floating point number will be converted to 4 as an integer, and square will return 16 for that. Now, if you were expecting the square of 4.5 to be 20.25, that is not going to happen. And so you'll get an unexpected, a wrong result. So these are things that you have to know and have to keep in mind. So converting from a higher data type to a lower type can change the data value, may even give you something wrong. And whenever that happens, many compilers will give you at least a warning. If you forget to provide a function prototype, the compiler will look at the function definition that you provide and insert a matching function prototype automatically at the beginning. You won't see that, but this happens at compile time. This too will throw up a warning or an error, depending on how the compiler wants to deal with it. As a rule, do not count on the compiler to insert automatic function prototypes. You should always include function prototypes for functions, especially the ones that you're making, the ones that you are defining. Finally, a function prototype placed outside any function definition applies to all calls to the function appearing after the function prototype in the file. Function prototypes placed in a function body apply only to calls made in that function.